Mm-hmm.
Can I get my last two test grades back, please?
Yeah, dude. Oh, hold on. Found them. Yeah, looking at these, you got 2 Fs on your last 2 test grades.
What?
Yeah, it's pretty bad. So, I pretty much know you need a tutor. So I've lined up 3 awesome girls that are going to help you out.
Okay, well, let's go to tutoring.
Let's go to tutoring.
So do you know what a proton transfer reaction is?
I'm sorry, what did you say?
A proton transfer reaction. Do you know what that is? Okay.
No.
Well, it's a reaction that consists of a single elementary step where a Lewis acid and a Lewis base react. And the Lewis acid is an electron receptor and the Lewis base is an electron donor. You might want to take some notes. So the acid becomes a conjugate base after accepting electrons, and the base turns into a conjugate acid when it gives away electrons. When the electrons move, we use a curved arrow going in the direction of the electron movement. So I'm going to show you an example of how electrons move from a base to an acid. And in this example, we have water and ammonia, and the ammonia has this lone pair up at the top. So these electrons are going to bond with the hydrogen, and the hydrogen can't have more than 2 electrons bonded to it, so its bond will break, and those electrons will go to the oxygen. So the water, which was an acid at first, will turn into a conjugate base because it has more electrons and it's missing the hydrogen. And the ammonia will be the conjugate acid because it accepted that pair of electrons as the hydrogen. So next, I'm going to talk about the KEQ, which is the equilibrium constant, and that is the reaction's tendency to form products. So you find that by doing the concentration of the products over the concentration of the reactants. And if you get a very large KEQ, it means you have more products, and a very small one, it means you have more reactants. If it's close to 1, it's closer to the equilibrium because you have about the same amount of products and reactants. Ka is the acidity constant, and that helps determine the strength of an acid. So the larger the Ka is, the stronger the acid you have. And Ka has a really wide range, so it's easy for the numbers to be really small or really big. So to avoid that, you use pKa, so that the numbers are easier to compare. And to find pKa, you do the negative log of the Ka. The least positive pKa you get is the stronger acid, and the more positive the pKa is the weaker acid.
Alright, Cade, are you ready to learn today?
I am.
Alright. So thermodynamics relates to Chapter 6 through the Gibbs free energy equation. And this equation is important for 2 reasons. Number 1, it shows the spontaneity of a reaction and the stability of the reaction. So this looks like a confusing equation. However, a lot of these are just constants and you plug it in. So R is 8.314, T is the temperature and it's always in kelvins, and the equilibrium constant is typically given to you, and if it's not, you can plug it in and solve for it. So this equation is important because it can show whether a reaction is spontaneous or not. A spontaneous reaction means it is a reaction that has tendencies to favor the products. So a spontaneous reaction that is less than 0, well, would be considered spontaneous. A reaction that has a delta G greater than 0 would be considered non-spontaneous, and the reaction does not tend to favor the products. This can also show you stability. So if a delta G is less than 0, products are more stable, and if it's greater than 0, products are less stable. Moving on to the next thing, enthalpy and entropy. Enthalpy is heat, and entropy is the measure of disorder in a reaction. So delta G equals delta H minus T delta S. In this equation, if the delta H is positive, that means the reaction is endothermic and it means it is absorbing energy. If the delta H is negative, that means the reaction is exothermic and the reaction is releasing energy. Typically, entropy is a small number in this equation and does not have a lot of significance in a proton transfer reaction. In a free energy diagram, we have reactants, a transition state, activation energy, and products. What's important to remember in a free energy diagram is that in order for the reactants to form into products, it must surpass the transition state energy, and it must have enough energy to get over this hump in order for it to become a product. So now we're going to talk about functional groups and how they relate to acidity. What you need to do is remember two things. Acidity is governed largely by functional groups, and you also have to look at the structural features of atoms near functional groups. So things like highly electronegative substituents or the presence of double bonds can highly affect whether or not your functional group is the same as the table in 6.1. So in these two examples, we have ethanol and propan-2-ol. So your OH and your OH are similar, and your CH3 and your CH3 are similar. There are no highly electronegative atoms or double bonds, so your pKa is going to be pretty similar, 16 and 16.5. In this example, you have trichloroacetic acid and then just acetic acid. So here, though, the biggest difference is you have a trichloride right here. This Cl3 is a highly electronegative atom, which is going to make this an acetic or more acid compound, 0.77 pKa, and this is going to be more basic, 4.75.
Which one's stronger?
This one.
Oh,
Got it, Cade?
got it. Hey, can you tell me something about charged species?
Yeah!
Oh, great.
So a charged species is significantly higher in energy, which makes it less stable.
Really?
Really.
Less stable if it's
Yeah.
higher, okay.
So the further to the right an atom is on the periodic table, the more acidic the proteins are that are attached to it.
Okay, cool.
Stability of an anion increases when the negative charge is on the atom further down the column of the periodic table.
Further down?
Further down.
Okay. Man, I had no idea.
Do you want to learn a little bit about delocalization?
I really do. I really do.
Okay, so delocalizing a charge via resonance lowers the concentration of the charge and increases the stability of the charged species.
Does it say that in the book?
It does.
Only if I'd read.
Stabilization via resonance generally increases the number of atoms over which a charge is delocalized. Okay, so we're going to do some examples. We need to rank these four compounds from highest to lowest pKa. And we did that because the higher number of chlorines that you get, the lower the pKa goes. And this is because the lower the pKa, the stronger the acid. So the highly electronegative atoms stabilize the conjugate base, making ionization occur more readily. So you would have, this would be your highest pKa because it's the least acidic, and as you get more chlorines, it gets, the pKa gets lower. Okay, this is going from strongest to weakest acid, and this is based on the electron withdrawing inductive effect. So the more fluorines, the stronger the acid, because fluorines, the electron withdrawing effect is going to be very strong for fluorine. So cool. The more you get, the stronger it is. Okay, that's all for now.
Thank you. I learned so much during my time of getting tutored. I know for a fact I can make an A on the next test. Some of the things that I learned were how to determine pKa and Ka and how they correlate with one another. I also learned the equilibrium constant. I learned how to rank the strength of a molecule based on pKa or Ka or the size, radius. I also learned how to move electrons around and the proton transfer reaction. I learned how to interpret a free energy diagram. I learned thermodynamics. I even learned functional groups and their relation to acidity. I know for a fact that I just killed that test that I took.